Welcome to the Deep Dive, our segment here at Science Corner, where we really get into the research that's reshaping how we see things.
It's always exciting to explore these frontiers.
Today, we're tackling something truly fundamental. It might just rewrite physics. The topic is three-dimensional time, a framework for fundamental physics.
Ah, yes, a fascinating concept.
We usually think of time, as this single arrow just marching forward.
Relentlessly forward, yes, that's the standard picture.
So what if that's incomplete? What if time itself has dimensions, like space does?
That's the provocative idea here. Multiple dimensions of time.
We're diving into a paper by Gunther Kletečka, published just last year, 2025, in Reports and Advances of Physical Sciences.
A very significant publication.
Our mission today: unpack this idea, understand what it claims, and, crucially, how it might solve some huge puzzles in physics.
Things like particle generations, quantum gravity, the big ones.
Exactly. And what's really striking, as you mentioned before we started, is how it challenges our basic intuition.
It really does. It forces you to ask, what is time? Fundamentally, how does it shape reality? It pushes those boundaries.
And importantly for you listening, this isn't just some abstract thought experiment.
Right. Not at all. That's the key.
This framework makes real, concrete predictions, testable ones.
And testable relatively soon, with experiments that are already running or coming online.
So we might actually see evidence for extra time dimensions, potentially in the next few years.
That's the exciting possibility, yes.
Okay, let's get into it. Three-dimensional time. It just sounds, well, mind-bending. Time is just time, isn't it? How does this framework picture it?
Well, the core idea is moving beyond the familiar four dimensions, three of space, one of time.
Our standard space-time.
Exactly. This paper proposes a six-dimensional reality, a six-dimensional manifold, technically speaking.
6 dimensions, so the usual 3 space dimensions, X, Y, Z.
Those stay the same. Your familiar spatial coordinates, but then instead of one time dimension, it posits three.
3 separate time dimensions, okay. T1, T2, T3, I think the paper calls them.
That's right, T1, T2, and T3. And the crucial point is that this isn't arbitrary. It's not just, let's add more time.
There's a reason for exactly 3.
Precisely. The paper argues it emerges from fundamental symmetry principles in physics, and perhaps more compellingly, from observed transitions at 3 very different physical scales.
Different scales. So these time dimensions aren't all the same. They do different things.
Exactly. They correspond to different domains of physics. Think of them almost like different gears driving the universe at different levels.
Okay, can you break that down? What does each one govern?
Sure. Let's start with T1. This one operates at the very smallest scale, the quantum scale.
Like Planck scale small.
Yes, Planck time scale, where quantum mechanics reigns supreme. T1 is fundamentally linked to quantum behavior, particle interactions, and even how particles get their mass.
Mass generation comes from a time dimension. Wow, okay.
What about T2?
T2 is described as the interaction scale. It sort of mediates between the quantum world of T1 and our more familiar classical world.
A bridge, almost. In a way, yes. It's crucial for understanding why we see distinct particle generations. The electron, then the heavier muon, then the even heavier tau.
Ah, the 3 generations. The standard model lists them but doesn't really explain why 3.
Exactly. This framework suggests T2 is key to that. It's also central to the weak nuclear force, the one involved in radioactive decay. It's where certain quantum effects make finite corrections that bubble up to larger scales.
Okay, T1 quantum, T2 interaction generations. That leaves T3.
T3 operates on the largest scale, the cosmological scale.
So galaxies, universe expansion, that sort of thing.
Precisely. It governs the evolution of large-scale structures, and it's strongly linked to gravity, particularly how gravitational waves travel across the cosmos.
So if I'm getting this, these aren't just math concepts. They map onto real physical processes at different levels. Quantum, particle interactions, and cosmology.
That's the core claim. They are distinct dimensions tied to distinct physical regimes.
And that explains why we usually only perceive one dimension of time, because the effects of T2 and T3 are only really obvious at extreme scales.
That's the idea. In our everyday experience, the effects are subtle or averaged out, but the framework goes even deeper, philosophically.
How so?
It suggests that matter and energy aren't just things existing in time. Instead, matter and energy might be manifestations of the structure of these time dimensions themselves.
Wait, so time isn't the container, it's the substance.
That's the provocative reframing. What if time is the fundamental stuff and everything else emerges from its structure?
That's a lot to think about. How does this compare to older ideas like Kaluza-Klein that also used extra dimensions?
Good question. Kaluza-Klein theories typically added extra spatial dimensions, small curled-up ones, to unify forces.
Right, hidden space dimensions.
This approach is different. It uses temporal dimensions. And importantly, the paper argues this specific structure avoids major problems that plagued earlier multi-time theories, like violations of causality or instabilities.
Meaning cause still comes before effect. Things remain stable.
Yes, those fundamental principles are preserved. And it doesn't need extra spatial dimensions or complex mathematical add-ons. It aims for a kind of parsimony, building just from these three times.
Okay, building from those time dimensions, let's talk math for a moment, but keep it accessible. How does adding these extra times stay consistent with physics we know works, like general relativity or quantum field theory?
It hinges on the mathematical structure, the metric it defines for this six-dimensional space-time.
The metric being the rule for measuring distances or intervals in this combined space and time.
Exactly. The equation is ds2 equals dt12 plus dt22 plus dt32 dx2 dy2 dz2. Notice the signs.
Ah, plus signs for the time dimensions, minus signs for space. That's different from standard relativity's 1 plus and 3 minuses.
It is. That specific signature, plus big sig, plus tau, plus theta, is crucial. The paper shows it's necessary for maintaining consistency, ensuring things like positive energy.
And you mentioned causality and stability. How are those preserved?
The framework is constructed specifically to maintain causality, no time travel paradoxes, and unitarity.
Unitarity. That's about conserving probability in quantum mechanics, right? Things have to add up properly.
Precisely. It ensures quantum mechanics still works reliably. These were big stumbling blocks for previous theories with multiple times, but this structure seems to navigate them.
So it doesn't just throw out the rule book.
Not at all.
Yeah.
It extends it. Take general relativity, Einstein's theory of gravity.
Our best description of gravity on large scales.
In this framework, GR emerges naturally as a limiting case. If you're looking at situations where the effects of T2 and T3 are very small, negligible.
Like in our solar system, maybe?
Potentially, yes. In those limits, the equations of this six-dimensional theory simplify and reduce directly to Einstein's field equations.
So it contains GR within it. It doesn't contradict it.
It extends it.
Yeah.
The same applies to quantum field theory, or QFT, which underlies the standard model of particle physics.
The theory of all the fundamental particles and forces, except gravity.
Right. This framework uses extended quantum fields defined across all six dimensions. But again, in the appropriate limits, these complex equations reduce back to the standard QFT equations we know and use.
So it's like zooming out to a bigger picture that still contains the familiar details when you zoom back in. What about symmetries? Do we get new ones?
We do. Because you now have three time dimensions, you get new possibilities for rotations in time, just like you can rotate in space without changing the laws of physics.
Like turning an experiment around shouldn't change the result.
Exactly. This theory suggests you can have analogous rotations between the time dimensions governed by a symmetry group called SO3T.
Okay. And symmetries usually lead to conservation laws, right? Like energy conservation comes from time translation symmetry.
All right. So these new temporal symmetries lead to extended conservation laws. Energy momentum and angular momentum are still conserved, but now they account for flows across all the dimensions. And there's a prediction of a new conserved quantity, a kind of temporal charge.
A completely new conserved quantity. That's fascinating. Okay, this is where, for me, it gets really interesting. The claim is this framework doesn't just look consistent, it actually solves long-standing problems. Let's start with those particle generations. Why 3?
This is perhaps one of the most elegant outcomes claimed by the paper. The existence of exactly 3 particle generations isn't put in by hand. It emerges naturally from the structure.
How?
It comes from solving eigenvalue equations associated with the temporal part of the metric. Think of it like the 3 time dimensions can only vibrate or resonate in 3 specific ways.
Like modes on a string.
A bit like that, yes. And those 3 fundamental modes correspond directly to the 3 observed generations of quarks and leptons, electron muon tau, the different quarks, and so on. Their mass hierarchy is also linked to this structure.
So it predicts not just that there are 3, but maybe something about their masses, too.
It does. And the predictions are remarkably precise. For the top quark, the heaviest known particle, it predicts 173.21 plus or minus 0.51 GeV.
And the experimental value is?
Measured at 173.2 plus or minus 0.9 GeV. An excellent match.
Wow. Okay. Any others?
Yes, the muon mass predicted 105.6583745 MeV, measured 105.6583755 MeV with tiny error bars on both. The electron mass prediction matches the measured value perfectly within experimental uncertainty.
That's incredible, getting particle masses out of the structure of time itself.
It even predicts neutrino masses, which are notoriously hard to measure, predicting specific values for the different types, and mass ratios between generations, like 1 to 4.5 to 21.0.
Okay, that's a strong piece of evidence if those hold up. What about other puzzles? Parity violation? The weak force acting weirdly?
Yes, the fact that the weak force distinguishes between left-handed and right-handed particles, parity violation.
Why neutrinos are only left-handed, for instance.
Exactly. In this framework, that asymmetry isn't an ad hoc addition. It arises geometrically from the three-dimensional temporal structure. The mathematical object used to describe parity violation, the gamma-5 matrix, emerges naturally from the interplay of T1, T2, and T3.
So the weirdness of the weak force is actually a geometric property of time.
That's the claim. It even makes predictions for related effects like CP violation, the subtle difference between matter and antimatter.
All right, particle generations, parity violation. What about the biggest one? The unification of quantum mechanics and quantum gravity.
The Holy Grail. The framework approaches this through finite corrections.
Finite corrections, meaning it avoids the infinities that usually pop up when you try to quantize gravity.
Exactly. Many approaches to quantum gravity run into ultraviolet divergences, basically. Calculations blow up to infinity at very small scales or high energies. This framework, due to its structure, naturally regulates these calculations.
How? Does it introduce a smallest scale inherently?
The interaction scale associated with T2 seems to play a key role, introducing effects that prevent these infinities. It leads to a well-defined quantum theory of gravity, at least in principle.
So, a path to quantum gravity without infinities.
That's the promise. It also predicts specific energy scales, where these quantum gravity effects, or effects related to the new temporal dimensions, should become important. A modified Planck mass, around 1.22 by 119 GeV.
Still incredibly high energy, but specific.
And potentially a new scale around 2.3 by 104 GeV, or 23 TeV, linked to one of the temporal dimensions, which is much closer to energies we can probe. Also, unification scales for forces around 2 by 1016 GeV.
Okay, this all sounds incredibly elegant, potentially revolutionary, but theory is one thing. You mentioned testable predictions. How do we actually go out and look for evidence of three-time dimensions?
This is crucial. It's not just philosophy, it's physics. The predictions are concrete and, importantly, within reach. We're talking the 2025-2030 timeframe for potential signals.
So what are we looking for? Where?
Several places. In particle physics, the most direct search is for new particles.
New resonances, you called them.
Yes. The theory predicts new, heavy particles should exist with specific masses. One around M1 goes 2.3 TeV, plus or minus 0.4 TeV. Another around M2 equals 4.1 TeV, plus or minus 0.6 TeV.
TeV tera electron volts. That's LHC territory, right? Large Hadron Collider.
Absolutely. The high luminosity LHC upgrade, which is ramping up now, should have enough energy and data to potentially see hints or even discover the M1 particle with solid statistical significance.
And the heavier M2?
That might require the next generation machine, like the proposed Future Circular Collider, the FCCHH, expected around 2040. But finding M1 at the HLLHC would be huge.
Any other particle physics signals?
Yes, precision measurements. Things like how neutrinos oscillate, change types as they travel. The framework predicts specific patterns in those oscillations and in related CP violation effects.
And experiments like DUNE are designed to measure exactly those things. Yeah.
Exactly. DUNE, Hyperkamiokande in Japan,
Yeah.
they will provide crucial tests.
Okay, particle colliders and neutrino experiments. What about gravity? You mentioned T3 was linked to gravity and gravitational waves?
Yes, the theory predicts subtle modifications to gravitational waves as they propagate across the universe.
Modifications how?
Two key things. Slight deviations in their speed compared to the speed of light. Very tiny, predicted around 1.5 parts in 1015, but potentially measurable.
Wow, that's precise. How could we measure that?
By comparing arrival times of gravitational waves and light or neutrinos from the same cosmic event, like a neutron-star merger. Also, the theory predicts unique polarization modes for gravitational waves.
Different ways the waves can stretch and squash space-time.
Exactly. Modes that are forbidden in standard general relativity, but allowed in this three-time framework. Detecting those would be a smoking gun.
And our detectors, like LIGO, Virgo, K-GRI, and the future LISA space mission, they could see this?
Advanced LIGO Plus and especially LASA should have the sensitivity to probe these predictions. It gives us a clear way to distinguish this theory from standard GR or other modified gravity ideas.
Particle physics, gravitational waves, anything on the cosmological scale, T3's domain.
Yes, cosmological signatures. The framework influences the expansion history of the universe.
How? Through dark energy.
It predicts a specific equation of state, for dark energy basically, how its pressure relates to its density that changes slightly with cosmic time in a particular way. The prediction is WZ, nice 1 plus 0.05, 0.01, 1 plus C3.
Okay, that's specific, and something telescopes can measure.
Yes, missions like the Euclid Space Telescope already collecting data and the Vera Rubin Observatory coming online soon are designed to map the expansion history and large-scale structure with incredible precision.
What about structure formation, how galaxies cluster?
The theory also predicts subtle modifications to the matter-power spectrum, which describes the distribution of matter on large scales. These deviations could be detected by those same large galaxy surveys.
So looking at the biggest structures in the universe could also reveal the structure of time itself.
That's the idea. Taken together, these predictions across particle physics, gravitational waves, and cosmology are like unique fingerprints.
Not just finding something new, but finding these specific predicted signals.
Exactly. They provide clear experimental handles to test the theory and distinguish it from alternatives.
It really is exciting. The possibility that experiments running now or starting very soon could fundamentally change our understanding of time. It's quite profound.
It feels like a potentially pivotal moment in fundamental physics.
So, just to wrap up, we've discussed this framework proposing 3 dimensions of time, not just one.
Correct. A 6-dimensional manifold, 3 space plus 3 time.
And it's not just a mathematical curiosity, it aims to unify quantum mechanics and gravity.
By providing finite quantum corrections for gravity.
It naturally explains why we see 3 particle generations and their mass patterns.
Emerging from the temporal structure itself.
It accounts for peculiarities of the weak force, like parity violation.
As a geometric consequence.
And critically, it makes specific, testable predictions that we can look for in the coming years.
Across multiple experimental frontiers, yes. What this framework really suggests, if it holds true, is that time isn't just this passive background, this river we flow down. It's an active, dynamic, multidimensional player in how the universe works at its deepest levels.
A fundamental substance, almost.
Perhaps. Its mathematical consistency is strong, its explanatory power for existing puzzles is impressive, and the fact that it offers concrete tests. That really elevates it as a serious contender for a more fundamental theory.
It moves beyond just concepts to things we can actually go out and measure.
That's the key difference.
So here's a final thought for you to take away. If our universe does have 3 dimensions of time, what else might that imply? How might that change our perception of reality, cause and effect, maybe even consciousness? What other secrets could be hidden in these extra dimensions of time? Thank you for joining us on this deep dive into what might be the future of physics. We encourage you to keep exploring these fascinating frontiers